Okay. Right. So the physical part, right? The jumps and all the physical exercising, that's still part of the session. So if you didn't do any of the jumps and so on before we look at the problems, you should do this after the discussion. But that's sort of obligatory part that you have to do. Okay, so this is a reminder of where we are, right? So we are talking about variational problems, discrete and continuous, and we have two objects that we're playing with, right? So we have some kind of double integral, right? Which to us is really just a functional on measures. So this really just takes mu and sends it to double integral like that, right? So that's one object that we're considering. And the second is a functional on collections of points. So equivalently, you could think of it as a functional on discrete measures, something like that. And what it does is it takes a collection of points and forms a sum like this. And the points run over this configuration, discrete configuration of cardinality n. And so I'm assuming here that the set A is an RD, and so is the omega n.
What happens? Sasha, you muted. You muted.
Okay, now I have to start from the very beginning, right? Okay, so, all right. So the discrete object is rather hard to study by itself. It has a lot of local minima and so on. So to make things a little easier, we take n to infinity and then prove something like gamma convergence, which was, by the way, mentioned by Gera today, and maybe was mentioned previously as well, but at least once it came up today. The point being here that, okay, maybe this is a very complicated object, but once you take large n limit, you come up with something simpler, hopefully even convex in a certain sense. And conversely, this may be a difficult object to deal with numerically, and you want to do it, and so maybe you discretize the double integral and you look at the sum, right? So we're interested in this interplay generally. Okay, so that's the overall setup. Right now, I want us to focus on this guy, specifically on this condition that Ed has stated maybe once or twice, and Sylvia stated once today, I believe. And it's a simple variational condition. That says roughly the following: if you have a functional, right, which sends, let's say, probability measures, so mu is a probability measure supported in our fixed predetermined compact set A, and it sends mu to this double integral. And then you can perhaps add some sort of external field if you feel like doing that. So there could be something like this as well. And let's say mu lives in a compact set A, or maybe the potential is confining or some such condition to make sure that the optimization problem is well posed. Okay. So what does Strassmann condition for this functional say? Well, it says that if you have a minimizer, so if, let's say mu0 is a global minimizer, let's say, then the following conditions hold. So basically, the potential of this measure mu0, right, which consists of two parts. This is a single integral of k xy with respect to mu, and this is the same v as before. So this is at least some constant on quasi everywhere on, let's say, A, assuming we're optimizing over measures on A. If not, it's quasi everywhere on the entire space. And on the other hand, this same potential is at most the same constant everywhere on the support of mu. Right, and quasi everywhereness means okay, so this holds for some, maybe I should say for some C. It's not terribly difficult to see right away that the C has to be the value of the minimum of our functional, right? So exactly the value of this functional on mu0. Okay, and so quasi everywhereness means up to, let's say, sets S for which mu support of mu lives inside S implies mu is sent by our functional to plus infinity. Right? So the arrow is the same arrow as you have seen up here. Same arrow. So in other words, up to a set of zero capacity, so set that cannot hold any positive fraction of your measure. Okay, and so this is all very nice, and obviously not hard to derive, as you probably know, and you may have thought about this. Okay, what about this quasi everywhere? Can we get rid of it, right? And the easy answer is, okay, well, when the kernel is nice, when the kernel is continuous, this is trivial, right? You can drop this condition right away. If let's say the kernel is when the kernel is integrable Ries, so x minus y distance to the negative s with s less than the ambient dimension, you would expect, okay, this is a nice functional, nice kernel. Certainly something can be said about this. So that's where we are going. Okay, so I would like to state, maybe sketch how you would prove something like how to drop quasi everywhereness. Right, so question. So answer, for instance, if K is a radial kernel, let's say it's a function of distance, right? And it behaves nicely. So with f, so here is a nice function. So it has to be, let's say, continuous apart from 0. So I'm stating some kind of conditions. It's an exercise to relax as many of them as possible. So basically, every word here is an exercise. right? So it's a nested exercise. It's you see how it goes. Let's see. For some positive epsilon, and maybe some t epsilon, which is also positive, the function, or let's say the product t to a d minus epsilon, f of t is increasing on. Okay, and this is, oops, and this is understood as, so the value at 0 is understood by taking the right limit. So the value of f at 0 is just the limit from the right. And so we call such kernel. So this is the definition. It's a d-Rees-like, right? So this is just a way to slightly generalize kernels of the form. So for instance, anything of the form x minus y to the negative s with s in this range is okay, right? So another exercise, what other kernels work, right? What else can you come up with? Okay, and here's a theorem. So suppose A is, let's say, d-regular set. So I will tell you what this means in a second. So basically, a set which is locally not too big. I should maybe say compact set and so on, but you already know that. Okay. So kernel is d-Rees-like. And this part of the potential, right? So I call this is single integral of the kernel with respect to a measure, right? So this mu. Let's see. So this here satisfies.
Sorry, one question.
Yes.
What are you doing on the v second?
Okay, sorry, I could not hear that.
What are you assuming on the v second?
Okay, so v is just this additive term. Let's say it's nice and continuous, right? So that the difficulty boils down to this guy.
Okay, so the only differentiability that needs continuity. So,
okay, again, I did not hear that, but I think we can agree that the main difficulty lies with this part, right? The additive guy adding the v is okay. Well,
I mean, if it could be infinite, then you run into problems. So for sure, it was that's fine. Other than that,
what can be infinite?
If v could be infinite, then there could be mass concentrating on measure zero sets. Of course, it's a pathological case, but that just got me wondering what else do you need on v?
Right. Okay. Yeah, that's a good. That's certainly a very good observation. So this guy here should.
Well, okay, if you assume that.
So let's say there's a sublevel set of V. Okay, let's say there's a sublevel set of V which is closed and deregular. And again, I'm going to tell you what deregular is, right? Or let's say V is 0, and then we'll just prove this theorem, and then you add V, and it will be more or less clear how to handle the complications with V. Because again, the primary issue here is we have a kernel with singularity. We'd like to understand what this integral potential does. Right, so I agree with your observation. You're exactly right. We have to say something about V, but my point is, well, that part should generally be easier than the integral.
I'm satisfied.
Great, excellent. All right, so suppose you have an equality of this form that holds quasi everywhere on your set A, and maybe A is, again, it may serve as a sublevel of B or whatever. And this inequality holds quasi everywhere, then, so this is the conclusion, this actually holds everywhere. So how do you prove something like this? There are two options. You outline the idea, or you run the argument by it is late in the afternoon. So you know there is an argument by contradiction. There's also another argument which is called by, quote unquote, it is too late in the afternoon. So I'm not going to use the second one yet. So the idea is this. So every point of A is Lebesgue is a Lebesgue point. Oh, you see, I'm rushing forward. I'm sorry, I never defined what deregular means. But okay, let me finish this sentence. I'll tell you what deregular is. I promise to remember now. Is a Lebesgue point for U and mu k, right? And from this, you will see already that basically this is the condition you want for V. Right, so you're asking what kind of V's are acceptable. Well, basically, if V satisfy this, then we're good. And what I mean by Lebesgue point is slightly different from the usual. So if you know Lebesgue, if you remember what Lebesgue point was from measure theory, then you took it not so long ago, or you have a very good memory. Congratulations. So we're averaging around points of A, right? And we're averaging with respect to Hausdorff measure on A. Right, so Hausdorff, or okay, if you like, with respect to Lebesgue measures. So to us, it's the same. So maybe you can call it Lebesgue measure. Right, and let's see. So this is my average over the same set. So it's kind of a restricted Lebesgue point, right? So this is what you prove basically, and the proof is exactly well, it's a bit technical, but because it's too late in the afternoon. The idea is that because you have a singularity that is not too aggressive, you can integrate it, average it out, and then you're good to go. So let me see what I want to say here. DHD Y. Right, so you average around any point of this set A, and you get back exactly the value of your potential at the center around which you're averaging.
Now the definition of irregular.
Great. So it's very good that I have such attentive listeners. But it's too late. Look, it's so late. Do we need anyway? All right. So here's the definition.
You can just give the idea.
Idea of a definition. Okay, that makes sense. So A is deregular. Let's say there exist numbers, finite numbers, You look at A like that. Right, so again, you can think of this as the Lebesgue measure if you don't like Hausdorff. Although, why would you? Okay, so this is okay. This is small c, right? This is the small c, and this is the big C. Okay, and that's your deregularity. And actually, an exercise. This might be an exercise with a caveat, but I suspect that this is redundant, right? The lower bound is redundant, and so actually, this entire condition might even be redundant. Okay, I have to think about it. Okay, it's not redundant because generally you can do the same thing for A that lives in a higher dimensional space, but I think if A is in RD, which incidentally I did assume, then this entire condition actually is redundant. Okay, but that's an exercise. Right, so in RD, that just means A is doesn't have thin